I'm very happy to be a speaker at the non-commutative geometry seminar, and virtually at Washington University and on Zoom. So the title of my talk is Structures of Proper Lie Groupoids, and I want to talk about two papers that I wrote with collaborators. And the first paper is with my collaborator, Laura Skoll and Jordan Watts. And the second paper is with my collaborator, Chris Seaton. The first paper is already in the archives. The second paper will be in the archives probably by Monday. We are planning to submit it to the archives very soon. The reason why I'm giving a talk that relates to two papers is because the topics are not that dissimilar, and also I don't want to get into the nitty-gritty details of the paper. I just want to get the main ideas across, and then the people who are interested can go and look at the details in those papers. So let me start here. Okay, let's see. Okay, this is just an outline of the talk. I'll give some main definitions, which everybody knows, but just to set the notation, I will reiterate them. And then I will talk about the first results, which are relative to Breton homology and cohomology for transitive groupoids that are also properly. Really, in all of my talk, all of the groupoids will always be properly unless otherwise said. And this, as one might intuitively think, reduces down to the case of a group action, because the transitive groupoids on an orbit will act very much like a group action. And so the categories will be equivalent, but to actually do all of the details, it takes a while, and that's the reason why we wrote a paper. Then the second paper is joined to Chris Seaton and will relate to groupoid Euler characteristics, and again, properly groupoids Euler characteristics, and it will also be related to some subgroupoid of the group, the initial groupoid called the inertia. Actually, I will give you that terminologies later. They are quite technical definitions, so we use specific names. And the main result here would be that the Euler characteristic of the groupoid, what we define to be the Euler characteristic of the groupoid, would be the Euler characteristic of this inertia space. So let's get down to some details. Okay, sorry, here I jumped. Okay, let's see if I can do one page at a time. Okay, this, everybody knows what a Lie groupoid and a proper Lie groupoid is. Just to set the notation, a groupoid is a generalization of a group, and you have a source map that tells you what the source of an arrow is, a target map which tells you where the target of an arrow is, and you also, in the case of a group, you only have one object, G lower 0, which is the unit space of the groupoid. So there is always one target map and one source map, that just the map that sends every element in the group to a point, this point in G lower 0 that is in the unit space of the groupoid. Then we define the isotropy at a point in the unit space as the source comma target inverse of XX, that is the arrows that start at X and end at X. And in case we have a Lie groupoid, all the maps are smooth, and proper means the ST map is proper. So this is just the definition. Okay, let's see here. These arrows don't seem to work. Okay. What's a translation groupoid? A translation groupoid is an example of a groupoid in where the groupoid comes from an action. In the stock, all the actions will be written on the left. So it comes from an action of a group G on a manifold M or on a topological space M, depending which context we are in. Usually in the stock, G will be a compact group and M will be a compact space, but not always. And for example, this is a main example that is very simple. If you take the action of the circle, the group, the circle, the unit complex numbers, on the two sphere by rotation about a vertical axis, then we have that in this case, this is a group action. We'll use this example later. That's why I'm going over this. And it forms a groupoid. The groupoid is formed by the pairs G comma X, where X is an element of M. And we could also restrict actions and form restriction of groupoids as well. So let me motivate a bit the Braddon. Why did we want to do Braddon cohomology or homology for compact, for groupoids? That's the main idea behind this. We couldn't really realize we couldn't really do this except for the transitive case. We are still thinking about doing it for other cases. That's work in progress. But let me explain why we decided to tackle this particular problem. Braddon homology and cohomology is classical for compact group actions as developed, for example, by May and other people. I mean, Braddon, of course, and we used the reference by May. And Skoll and Pronk applied the above construction to the case of orbifolds. Orbifolds are particular group action in where the stabilizers are particular compact group actions, let's say, in this context, in where the stabilizers are finite. So they use the standard Braddon cohomology for compact group actions and apply them to the case of orbifolds. And they had some equivalence of categories. And so because of that, sorry guys, I didn't mean to shift anything. Because of that, both, we are all very interested in orbifolds like Skoll, Pronk, myself, and then Jordan Watts as well. And so we wanted to deepen this understanding and perhaps generalize this Braddon homology and cohomology to more general groupoids, not just the groupoids that correspond to an orbifold, which, as I was saying before, correspond to actions of compact groups with finite stabilizers. We wanted to see if we could extend those definitions. And also, we wanted to try to prove, once those definitions will be extended, Morita invariance, which is a property that orbifolds do have. So that's the goal. And so far, we are only been able to do this if we restrict to proper, of course, properly always, but transitive groupoids, which are very special case. So what's a transitive groupoid? Well, it comes from a transitive action of a groupoid, say. So we take a groupoid and we make it act on a space. How does a groupoid act on a space? Well, it acts very similar to the way a group acts on a space, but not every arrow acts on every point of the space. You have an anchor map that tells you which arrows will act on which points. So you take this definition of action of a groupoid on a space and you call it transitive if it is transitive, meaning the orbits are the whole space. So for this special case, for this type of very special actions, like transitive groupoids, which means the groupoid acts transitive on its unit space, acting transitively on spaces, so that's a really special case, we could do it. And so that's the first result I would like to present. let me explain a little bit how this is done in analogy with the compact group action case. You need to define something which is called the orbit category. The orbit category intuitively is the set of all orbits with a little bit more of a structure, but intuitively is the set of all orbits. And in the case of a compact group action, say, a transitive compact group action, which is the case of reference here, what are the orbits? Well, we know that an orbit is G over the stabilizer of G at a point, so G over Gx. And so that's what an orbit is, in this case, a transitive orbit, an orbit of a group action. So similarly, well, actually, let me explain it again. So the orbits are of type G over H, where H is a subgroup of G corresponding to the stabilizer. And then what are the maps between orbits, like a G over H going to a G over K? Well, they are the G equivariant maps. So in this way, we form a category. This is classical. And what we did is practically do the same kind of construction in this transitive case, in where we fix a point in the unit space and we look at what happens above that point. And so we are able to recast the group situation in this groupoid situation by using this equivalence. And so that's more of an explanation of why we do of how we do this. As I said, the idea is quite simple, but the details are a little technical. That's why I'm not gonna give absolutely every detail. But if you take a space Y on this groupoid X, then Y over G, sorry, I should have put a G script here, not G like that. It should be a G script. Y over G, meaning the space over the action of the groupoid, will be homomorphic to YB, that is the fiber over B through the anchor map over GBB. And this doesn't need, Y doesn't need to be a transitive space here. It could be any space. So, you know, we have this correspondence between objects in the groupoid category and orbits there with objects in the group action category and spaces and quotients there. So that's more or less what this slide is saying in more technical terms. And we have to compute the set of equivariant maps from one orbit to the other. That's why we use this set of maps. And we had to recast them in the group version, which is more like this one to the right. Okay, maybe, sorry guys, I should close this window here. Okay, because you cannot see some of my slides. All right, so this is what I just did. Okay, so then you have to define something which is called the GCoefficient system. I mean, I'm not gonna give that many details on this. Again, it's a classical definition. What we do is first build a canonical G-coefficient system, which is practically obtained by a triple. You take X, you subdivide it as a GCW complex, in which case the definition needs to be updated to the groupoid level, but again, you could think of the group action level. And so it's a GCW complex. And then you take the fixed points, you know, remember one of those objects that are in the orbit category will be of type G over H. So practically this fancy notation means you do the fixed points of H, of the subgroup H, on the n skeleton or on the n-1 skeleton, and then you do the relative homology. That's a fancy way of writing it. I'm not gonna go into the details. I think the ideas are much simpler than how then in the end you're gonna write it down. And so you define this canonical G-coefficient system, then to define the cohomology in another coefficient system, you just take the hom over the orbit category from this standard coefficient system to another one. You find a complex. By the way, the D is related to the D to the boundary mapping triples, for triples. And then you do, you just do the cohomology. So, and this is how you do the homology, and by dualizing. That's all I want to really say about this. And the details are in our paper if you want more details. So this is more or less what I wanted to say for the Braidon homology and cohomology. A corollary is that in the case when the system of coefficients is a constant, then you get what you expect. Well, what do you expect? You expect the Braidon cohomology of X, the coefficients in this constant system, to be isomorphic to the singular homology of the quotient space. So that's what you expect. So this is the Braidon cohomology and homology part. Again, I'd like to emphasize that so far we've only been able to treat this very special case, but we would like to treat more cases. So hopefully we can advance our project and come up with other classes for which we can define the Braidon homology and cohomology. By the way, another remark before I jump to Euler characteristics is, because of the way we defined it, it is Morita invariant. But so in a sense, we succeeded in build Morita invariant theory, but because of the way we built it. So I'm not sure it's really, well, it's Morita invariant, but because of the way we built it. We would like maybe to have a more general definition and say, well, yeah, here is a Morita equivalence, and then we can show its Morita equivalence invariant, and not just because of the way we defined it. So let me now jump to the Euler characteristics and give some motivation for that. There has been a tremendous amount of work on orbifold Euler characteristics, especially for the case in where the orbifold is presented as space over the action of a finite group. That's a special case in where that you can define an orbifold in. So there has been a tremendous amount of work on Euler characteristics. They call them with all different names: orbifold Euler characteristics, stringly Euler characteristic. I mean, all sorts of different names. And the idea here, the motivation, is this. Guzzian, Zadel, Luengo, and Mellon-Hernandez extended some of these characteristics to nice G spaces X, where G is a compact Lie group. That was done recently, like I don't know, a couple of years ago, maybe. And so when we saw this, we thought, well, maybe we could extend it even further, because this corresponds to the translation groupoids G LF times X. So perhaps we can do it for more general groupoids, like proper Lie groupoids. Indeed, proper Lie groupoids, by the slice theorem, by several people, including Flaum, Postuma, and Tang, says that locally proper Lie groupoid looks like X left times G, like the action of a compact Lie group on a space times some other kind of more trivial groupoid. So because of that, we thought, well, since they defined these Euler characteristics for compact Lie group actions, perhaps we should be able to extend those Euler characteristics to the proper Lie groupoid case. And moreover, since we've been working a lot on this space called the inertia space, And we've seen that in the orbifold case, the Euler characteristics, some of the Euler characteristics defined for orbifolds were the Euler characteristics of the inertia space. We thought maybe we can also extend that result to proper Lie groupoids, that is, define this new Gaussian-Zada, Luengo, Meller-Hernandez type of Euler characteristics, and then show that they are the Euler characteristics of those inertia spaces. So that's the motivation, and that's what we actually did in this paper. And so some terminology here. We, instead of just, if one just considers the base case, one can take gamma to be the integer z. In order to write the paper and, do the, make the results explicit in the more general case, we use any discrete group gamma. Usually it's finitely generated. So what we do here is make these definitions that are in terms of a discrete group gamma, but you should really think of gamma as being the integers, because that is the base case, so that makes more intuitive sense. So the loop space is also called in some other references the isotropy subgroupoid. We consider it as a space, but it is a subgroupoid. Or G is the subgroupoid of all the arrows of type same range and same source, meaning they have the same range and the same source. Some people might call it a bundle of groups inside G. So it's the isotropy subgroupoid. And then you cross it by the action of G by conjugation, and then the space, what we call the inertia space, will be the quotient of this groupoid, the inertia groupoid, by the action of G. And there is also a map, I have to say this because we're going to use this later, from this inertia space to the orbit space of G on G0 induced by projection. So to make this a little bit more concrete, let me make the example in where this proper Lie groupoid is a translation groupoid, and so these things make more of an intuitive sense. So in this case, what we call the loop space, that is this isotropy subgroupoid, is the set of gx's such that gx is equal to x, so the pairs gx with gx equals x. What we call the inertia space is the quotient of this loop space by the action of G, which is by conjugation on the left and the way x on x on the right. So, and then the map A brings the pair, the class of the pair Gx to X. There is also another map that brings Gx to the class of G, which we are going to use in some other constructions that perhaps we'll get to. There is still 20 minutes, I might get to that as well. So there is this map, absolute value of A, and there's another map that instead projects to the first coordinate. For example, let's give a concrete example. If we take that example of the action of the circle on the two sphere by rotations about the vertical axis, then what's this loop space? Well, on the two sphere, there is no non-trivial isotropy, or the isotropy is trivial, so you just get the two sphere. And what happens at the North Pole and the South Pole? Well, at the North Pole and the South Pole, there is a full S1, sorry, I didn't write it as T1, but it's the same thing, a full circle of isotropy. So you are gonna attach that full circle of isotropy to the sphere at the North Pole, and similarly, you are attaching at the North Pole. So that's the loop space, the isotropy subgroupoid, viewed as a space. And then the inertia space will be that loop space modulo the action of the group. So on the S1, the action is by the adjoint action, so it doesn't do anything because it's abelian. And on the inertia space, sorry, on the sphere, you know, the action brings things around horizontally, so the quotient is a segment. So this inertial space is the segment with an S1 adjoint at the North Pole and one at the South Pole. And this map brings a pair, a point in the sphere to the segment. And of course, on the S1 is the identity. So let me cite some related work by start citing Flam, Postum, and Tang. They did some basic relative differential forms on the loop space, but as far as I know, maybe Shang can confirm this later, they didn't do any Euler characteristics, but they did certainly consider relative differential forms there. And this construction determined a shift of differential forms on the inertial space. And then with Chris and I have been investigating for the orbifold case. We never, I mean, in previous papers, we didn't investigate the case of a compact, I mean, not as much a compact group action and certainly not properly groupoids, but we did investigate the Euler characteristics of orbifolds in several contexts. And then I would like to mention the papers that Chris and I have joined with Marcos, in where we do go through a very detailed, explicit witness stratification of what we call the loop space and also the inertial space. So let me cite a result that we'll start with. If you have two Morita equivalent Lie groupoids, well, this is in the standard, with the standard definitions, then the gamma inertial groupoids, that is those groupoids I've been talking about before, are Morita equivalent, but not as Lie groupoids, because when we start looking at those inertial groupoids, they're not Lie anymore. They're actually what we call differentiable stratified groupoids, and we studied that in the paper with Marcos and Chris, but they don't have a Lie structure anymore in general. Maybe in some special case they might. And so, yeah, I mean, so this result of Morita equivalence is on that category of differentiable stratifiable groupoids or just topological groupoids, but it's not the level of Lie groupoids. But this is important. We're going to use this later. Now let me introduce the main tool we are using here, the integration against the Euler characteristic. And this is taken from the paper I was citing before, in where they do this for the compact Lie group action. I don't know if people are familiar with this. I actually didn't know much about it. I heard about it, but I never really dwelt onto it. You know, chi is additive. Everybody knows that. The standard Euler characteristic, that's what I mean by chi. And if, you know, you can define this in quite a lot of generality. For this talk, I'm not gonna give the most general setups possible. In the paper, we will dwell more on that. But you can take open intervals and consider them to be cells if you are considering, for example, semi-algebraic sets and the structures associated to it. And so you can, if you define the chi of an open interval to be -1, then chi of a half closed-in interval is going to be 0 by additivity. So this is not the standard homotopy invariant Euler characteristic for non-compact sets, but this is what makes it work. It's finitely additive, but not countably additive. So it's a little bit like a measure, and that's why you can integrate against the Euler characteristic. So how do you integrate? Well, you integrate functions from x to z that are bounded. So you only integrate functions that have finitely many values because of this finite additivity. And you integrate like you expect, like the sum of the standard Euler characteristics, or in whichever category you are, of the pre-image of a point in Z. So for example, if you are integrating 1 in the chi, that's by definition, you know, because of the above definition, is chi of the pre-image of 1. Well, the pre-image of 1 is the space X you are in. So that's chi of X, that's what you want. So if you're integrating 1 over a set, you get the Euler characteristic, that's it. And there are some properties on this integration, like if you chop off the domain into disjoint sets, then you get the sum of the pieces, you know, as you expect. So that's what allows us to define the Euler characteristic for this groupoid case. Again, if you don't like the gamma, just think of gamma as being Z, and that would be a special case. So chi of the homomorphisms from gamma to GXX over the adjoint action, I mean the action or conjugate action of GXX, d chi G of X over the orbit space of G. Well, this might not seem very intuitively, but if you look at the, perhaps if you look at the expression for a translation groupoid down low, maybe it's a little bit more intuitive. You take the stabilizer of X, of a point X, you divide out by the adjoint action, and then you integrate over M over G. So this, by the way, is the case of a group action, and by the theorem of Fromm, Postman, and Tang's Lie's theorem, then this is a finite, in the general case, we just have a finite sum, so terms like that. Well, it might not seem very intuitive, but why am I doing that? Because we are able to show two main results. That one, first of all, that Euler characteristic defined in that way, in the case of group action, is the same as the Euler characteristic defined previously by Guzzi and Zadai collaborators, even though they don't look the same. I haven't showed you what their characteristics looks like, but they don't look the same. But we are able, by using Fubinis' theorem, to prove that they are the same. And again, by using Fubinis' theorem, we're able to prove that the Euler characteristic defined that way is the Euler characteristic of the inertia space. So that was our goal. So even though it might not look intuitive that that's the case, that's what works. So let me go through Fubinis' theorem, which is really one of the main tools in our proofs. This is not something that we did. This is something that has been done in the literature. And so what we have here is that if we have a function from X to Y and then a function from X to Z, we can integrate in stages, like Fubinis' theorem. So the motivation for this is that if we take phi, let me just go to the case, you know, through the case in where X is a product, which is the motivating case. If X is the product Y times Z, then the projection, and then I project down using the projection on Y, or the obvious projection on Y, and I take the function to be the identity. What I expect to get is integral over 1 of d chi x on X, meaning characteristic of X. I'm expecting to get characteristic of Y times characteristic of Z. And if you go through the calculation, it's not that long, it gives you that. So it definitely generalizes, this Fubinis formula generalizes the obvious formula for the multiplication of the Euler characteristics that you have in the product case. So, okay, this is just a reiteration of the Euler characteristic of proper Lie groupoids. I could give here the formula of Gaussian-Zadel, Luengo, and Mella-Hernandez. It looks different. That's why our result, that those two Euler characteristics are the same, is one of the two main results of the paper. I mean, maybe the three main results. And so they don't look the same, you know, they look quite different, but by an application of Fubinis theorem, which I'm not gonna go through because it would take some technicalities, I would rather go through another proof, which it still involves Fubinis theorem, so has the same flavor, but it's a little bit maybe less technical. So you apply Fubinis theorem to this projection one, and you know, you do few equations. I mean, you write down a few equations, use some properties, and you get it. So let me now present this result, which is also one of the main results, but that says that in the Euler characteristic we define is the Euler characteristic of this inertia space. And I will go through the proof of this in the case of a translation groupoid. So that's why I'm not gonna go through the proof of the other result, because the idea is the same, use Fubini, but apply to a different map, of course. So this is one of the main results. So here we are. I wrote down everything in the case of a translation groupoid to make it more understandable, and in the case with gamma z, so to make it again more understandable. Of course, in the paper we have the more general case, but there is no point doing that in the talk. So remember I told you there was this map, absolute value of A, that brings Gx, the class of Gx, to the class of X. So that's what we are going to apply Fubinis theorem to. So you apply Fubinis theorem. First you start with the characteristic of this inertia space. That's the notation for the inertia space, the bars. That is, the characteristic of the inertia space is the integral of 1 over the inertia space. You know, that's what I said was true when you integrate against the Euler characteristic. And then you apply Fubinis to this map. So if you go and look it up, unfortunately, I cannot have two slides at the same time, or I don't know how to do it. What happens is that here you take the pre-image of A of a pair, and then that gives you Gx, the stabilizer of the other Gx. So you have chi, because you're integrating 1 of the Gx over Gx, and, and then here you have that this is exactly how we defined it to be chi of the groupoid in this special case. So that's it, the proof is finished. And in the general case, it is not much longer than this, but you just have to use the fancier notation with decorated by gammas and various other things. So a corollary, this is also an important result of the paper. A corollary is the Morita invariance. So if you have two Morita equivalent co-compact, we need this hypothesis of co-compact, properly groupoids, then their Euler characteristics are the same, because we know, as I told you to notice before, that the inertia spaces are Morita equivalent. Not Morita equivalent, I'm sorry, the inertia spaces are homeomorphic. And so they have the same Euler characteristics. That's what happens. So it's enough for them to be homeomorphic. You don't need them to be Lie groupoids. They're just homeomorphic because of the Morita equivalence of those stratified differentiable groupoids. But that's enough. So this is one of our main results, together with the previous one. And our Euler characteristic is the same as the Gaussian, Zada, and collaborators' Euler characteristic. So let me just do an example before I close. In the action of the circle on S2 by rotations, remember the loop space we said was a sphere with a circle attached to the North Pole and one at the South Pole. The inertial space, which is what we are considering, is a closed interval with a circle attached at the end pole and the North Pole. And the Euler characteristic of the inertial space, that is of the interval with the two circles, is -1 because it's homotopic to the bouquet of two circles. If it's compact, I can use homotopic. So let's compute the two sides and make sure that they're equal, the two sides in the previous theorem. One side was, well, actually we start with the t acting on S2. So one side was the integral over m over g of this chi add gx over a joint action d chi. But what was m over g? That's the inertia, sorry, m is S2 in this case. That was the inertia space. M over g was a segment to two S1s attached at the extreme points. And I'm sorry, say this again. M over g, m is S2. So m over g is just the segment. That's just the quotient of the action of the group on the space S2. So that's just the segment -1, 1, say -1, 1, if we take the unit sphere. So we are integrating over -1, 1 of chi of g of x over a g of x. So g of x is the stabilizer. So there are two different cases when the stabilizer is the whole of S1 or the stabilizer is just trivial. And so there are, if you see the integral is split in three parts, the first and the last are the integrals where the stabilizer is the whole torus at the north and south poles. And the middle one is the integral over the region where the stabilizer is just the trivial group 1. And so you have 1 over 1. And so we do get the first integral gives you 0 because chi of the torus is 0. The last integral gives you 0 because chi of the torus is 0. So the only thing that is remaining is chi of -1, 1, which is an open interval. So chi of it is -1 times 1, so that gives you -1. But that's exactly what the Euler characteristic of the space is, because remember the space is, the inertial space is a segment with two circles glued in one of the, at each of the two ends. So that's homotopy equivalent to a bouquet of two circles, hence is has Euler characteristic -1. So it checks out, good. I have another example, and with this I'm gonna finish. This is a little bit more complicated, but not too much. In this case, we take SO3 acting on R3 by rotations, and the quotient is the half open interval 0 infinity, parameterized by the distance r of points in the orbit to the origin. The isotropic groups of orbits corresponding to r greater than 0 is the circle, while the isotropic group of the points corresponding to r equals 0 is SO3, the whole thing. Then we split the integral into two parts. So again, we'll start with the integral m over g. M in this case is SO3. And so we have chi of 0, we know the 0, 1 times chi of SO3 over the adjoint action, plus chi of 0 infinity, chi of t. The part with the chi of t is 0. And so we are only left with the part that is not 0. And that is 1. And so in this case, what is the inertial space? Let's see here. Okay, we then write it down. Isotropic group, then this is that, and so on. Let's see here. No, didn't. Oh, okay, yeah, that's it. Well, I guess in this case we computed that the characteristic of the inertia space is 1. I'm not sure right now. I probably, need a few minutes to compute what the inertia space actually looks like. So let me just stop here and see if there are any questions.
Okay. Thank you. Do we have any questions or comments? So can I ask a question?
Sure, please.
So in your definition of the Euler characteristic, we do not need to assume the groupoid is co-compact, right? So
no, we don't.
We identified it with the classical Euler characteristic.
Right. I mean, the reason of the co-compact comes because we are really working in the paper on minimal structures, in particular the semi-algebraic sets. And so to satisfy some of the hypotheses that we put in the paper, we need compactness of the quotient space. But perhaps, one can get rid of it. But what I did here, it was just give an idea of what some of these concepts are. But to make it very precise, you need to actually choose a different category, like we work in a larger category. And so because of that, you need to satisfy some hypotheses in that category. I don't know, I think Chris, my collaborators, Chris Seaton might be listening in if he has anything to add, actually. You there, Chris?
Yeah.
Yeah, do you have anything to add to, to clarify our choices?
Yeah, no, so this Euler characteristic, it's defined for, I mean, we don't need compactness in order to define it, but I mean, basically exactly what you said, in order for it to line up with the classical homotopy invariant Euler characteristic, you need to assume compactness. And like the co-compactness is needed to express the integral in like a finite number of orbit space charts, but the general definition holds without co-compactness.
Yeah, actually, Shang, I'm kind of interested, because you did those differential forms, and, I was wondering, well, maybe can they get the same theorem? Because, when you consider differential forms, you can potentially get to Euler characteristics too. So I was kind of wondering if your construction will also get to the Euler characteristic of the inertia expressed somehow, maybe not in the same way we did.
Yeah, so just a remark, for our constructions, I think in order to get to the Euler characteristic, we'll probably need the co-compactness. Then we'll be able to say that the cohomology of this basic relative forms, together with the theorem differential in the properly defined, will have finiteness in cohomology. Then we can use the classical definition of alternating sum of the dimension. So I would guess that our definition using the basic relative forms probably will agree with yours in the case of co-compact groupoid. But in general, yeah, I have to think about how to extend our construction to your more general Euler characteristic as a distribution.
So do you have a notion of Marquis functor in this category of coefficient systems you work with? That, for example, in the case of compact Lie groups, maybe define.
I'll have to look this up. Sorry, I don't think we looked at this particular aspect, but that sounds very interesting.
Okay, so. Yeah, because in algebraic geometry also there's this notion of virtual Euler characteristic that is additive, right? That can be proven using Hodge theory, its existence. That I was wondering, I mean, you mentioned semi-algebraic sets, and I'm not familiar with the work. I'm just curious about it, so that's why I asked this.
Right. No, we haven't explored that avenue, but that's a possibility. But as I said, most likely our paper is going to be on the archives like by Monday, so you can look at the details of the category we are working in. But I definitely did not bring in all of those details in my talk.
But my curiosity about Mackey functors is that the homology and cohomology theory, Breton cohomology, can be generalized, you know, like Peter May schools, right? To a cohomology theory that's indexed by the, in the case of compact Lie groups, by the orthogonal representation ring, as pointed out long ago by Graham Siegel. But anyway,
that sounds very interesting. Thank you for mentioning this. We will look into it, but we have not looked into it right now. I cannot really answer the question, unfortunately.
Thank you. I enjoyed your talk.
Any other questions or comments? May I add one comment? So thank you for mentioning our work about the linearization of proper groupoids, but certainly, I mean, we are not the first group to work on this. So the original work actually goes back to Alan Weinstein around 2000. And then the general case was established by Zoom, I mean, around like, I think, early 2000. So our work is kind of after their works. So,
yeah, thank you for making that precise.